So I went to the public lecture titled Mysteries of Modern Physics, more specifically focused on time by Sean Carroll. Sean Carroll is a theoretical physicist that specializes in field theory, gravitation, quantum mechanics, just to name a few, and several others listed on his website. One of the first topics that he discussed was time and also the time's arrow or arrow of time. Um, it's something that he was very adamant about, and he states that time has a direction, but space does not, and the only way to tell the difference between the past and the future is this concept of the arrow of time. And he goes further into discussing it and saying that it has four aspects: aging, memory, free will, and cause and effect. Each are pertinent to either the past or the future. For example, memory. You have no memory of the future, at least nobody knows of which, and he made a joke saying that if anybody did have a memory of the future, please let him know, they'd make millions. Um, Free will, however, can't change the past but can only affect the future, so there is a contrast there of saying that there is one aspect of the time's arrow that focuses mostly on the past, while the other one can focus on the future. While he says this, and all these ideas are fairly obvious, not much people give much thought to it in much detail, so it's something that's not thought about a lot, and something that's imperative to what he believes is one of the key aspects of the Big Bang Theory. He goes on to say that fundamental laws of nature have no arrow of time, but simple motions do. They're not reversible is the key aspect. So simple motions like a pendulum, you can predict the past and the present based on that simple motion. There is no erratic event that could happen with a pendulum. It only goes swings forward and backwards, so it's something that's reversible. You can tell anywhere you stop on the pendulum which way it's going to predict, which way it will move based on previous and future events. He then moves on to talk about entropy, and this is the second largest topic of his lecture. And entropy was something that is the second law of thermodynamics, that things go from a low entropy state of something organized to a more high, very messy state. And it's a part of time's arrow as well. It's something that's not necessarily reversible. There is a relationship between time and entropy. As time increases, so does the entropy. So as time goes on, things become more chaotic, and it's very hard to reverse it, if not impossible. And Boltzmann first came up with this equation, and that there are more ways to have high entropy because there's so many chaotic situations than there are low. So there's the idea that yesterday always has lower entropy than today, and one of the biggest concepts of the Big Bang Theory is there are five levels or five time periods that they associate an entropy and an image with how much entropy and how far the Big Bang and how far the expansion of our universe is as we know it. So 1 second in, he showed us a picture of a white PowerPoint slide that basically symbolizes heat and even plasma. So it's one of the lowest entropy states that is possible, and as he said, the day before or the yesterday is always the one of lowest entropy. So going to 10 to the fifth years is a large timescale jump. So increasing entropy would create a picture of dispersion and several multicolored dots of cooling, which shows that there's increased chaotic nature of the universe, and showing that there's been an expansion of what had originally been just heat and even plasma. From there, 10 to the 10 years, we see that there are stars in the universe as we see it now, which is about what we think we're at this moment in time. 10 to the 15 years from the Big Bang, we predict that we'll start seeing black holes and stars will start to fizzle out. So entropy continues to become more chaotic, but at some point the energy is all gone and there's nothing but empty space, and it's hard to predict exactly what will happen, but 10 to the 15th years, that's their best guess of what they say. And 10 to the 100 years, it's empty space. It's called a Google, even though the search engine has taken that. Another joke from Sean Carroll. And it's just dark entropy. One concept to understand from that complexity does not necessarily equal entropy. While things are more chaotic and seem to be more complex, complexity first increases while entropy does, but then there is a decrease. So even with empty space, we can still have very chaotic and high entropy places, but the complexity appears to be very low, which is another key concept of his theory.